All right, so let's get going on today's class. So before we begin, just to let you guys know that exam 2 has been graded. We're just waiting on the makeup exams to be completed. Then we're going to take up exam number 2 in class and start preparing for exam number 3 today. So what we're going to do today is we're going to finally transition into the real world, no assumptions, know what's going on type of hypothesis tests. And we're going to start that by taking a look at chapter 6, which is the hypothesis test with means of samples. So this is going to finally complete your knowledge of the 5 steps to the hypothesis testing process, so that you can now do every single step all on your own. And specifically, this is going to address step 2, where you determine the characteristics of the comparison distribution. All right, so just a reminder, why are we doing this? Why are we working on inferential statistics? And it's important to keep this in your mind. What you're learning right now is what makes psychology possible. So the techniques that we're learning in this inferential statistics portion of this course is what allows us to go from the results of a sample of individuals and make conclusions about the population of individuals. So this is a very important aspect in psychology. If we couldn't do this intelligently, 2 things would occur. Number 1, we would just be doing guesswork. We would let our own personal biases, our own personal viewpoints influence how we were interpreting the data. And we would take a look at a sample. And if we were pro that result, we would say, oh yeah, our sample definitely generalizes to the population. And if we were anti that result, we would take a look at our sample and say, I don't think our sample would generalize to the population. I don't think it's a big enough difference to make that conclusion. So in this case of autistic children, if you developed an educational treatment for autistic children and you were pro inclusivity, you were pro having autistic children in the educational system, you would be biased towards looking at those results and saying that they support the fact that your educational treatment improves learning outcomes. On the other hand, somebody who was anti-inclusivity, somebody who did not want autistic children to be educated, would take a look at that same data, and by their own biases, they would say, no, this does not support generalizing to the population of autistic children. So again, we have statistics. We take that out of the hands of people with personal biases and allow us to come with a way of looking at a sample and generalizing about that population. So we are continuing our training to become statistics ninjas. We are so close to starting to do the real, actual things that we do in psychology, that professional people do in psychology. We are so very close to doing the actual tests that Dr. Ritchie and Dr. Rodriguez and Dr. Fujita and Dr. Ladd actually do when they analyze their research. And in getting there, we've been looking at kind of simplified versions. And you can think of this as you've been going through 5 steps of training. These are the 5 steps for a hypothesis test. And we are almost to the point where you will be ready to do all 5 of those steps and to do them all alone. So at this point, you now know how to do a hypothesis and a null hypothesis and research hypothesis for 1 and 2 tail tests. So you got step 1 down. You know how to find your cutoff scores on your distribution for a 1-tailed and 2-tailed test. You got step 3. You know how to calculate your sample z-score to find out where it is on the comparison distribution. You got step 4. And then finally, you know how to make that final decision of whether to accept or reject a null hypothesis. you got step 5. Up until now, the only step you've been missing is step 2, the characteristics of the comparison distribution. We're going to be doing that today, so you will have, after today, the complete set of skills to do any hypothesis test on your own. All right, so before we get to that, or in order to get to that, we're going to talk once more about samples and populations. Once more, we're going to talk about the distribution of sample means. And recall that this is very important because this is your comparison distribution. And then a new thing we're going to be looking at is determining the characteristics of that distribution of sample means. And it's been there all along, hidden in the central limit theorem, in terms of how do you go from a population parameters, knowledge about a population, and then determine the characteristics for that distribution of sample means. All right, so again, we've covered steps 1 through 5. You know how to do step 1, step 3, step 4, and step 5. And we were promising all the time that you would see how to do this in the next chapter, determine the characteristics of the comparison distribution. Well, the next chapter is going to be right now. So we're going to learn how we calculate the mean of that comparison distribution and how do we calculate the standard deviation of that comparison distribution. All right, so it all comes back once again to the idea of samples and populations, to that distinction between a sample that you have access to and a population, which is all of the subjects that satisfy a particular criteria. So all of the subjects in a potential population. And we almost never, and I really mean like never, ever, ever, ever have access to a population. So usually we're measuring samples and we use those samples to estimate population parameters. So we measure our 14 autistic children so we can estimate things about the population of autistic children. We measure our 20 depressed subjects so we can estimate things about the population of depressed subjects. You never get to work with all 1 billion, people in the population. You have to work with those samples. So we use, for example, the sample mean to predict what the population mean will be. And that's what we do in differential statistics as well. We use our measured sample mean to predict if there's a difference in the population means. So the challenge, though, is that if you don't know what your population is, then you don't know where your sample came from in that population. So most of the times in psychology especially, we're dealing with populations that we don't know what the mean of that population is. And we don't know what the standard deviation of that population is. So I just was at a conference where I saw a very interesting presentation where they measured people's judgments of whether or not something was sexual harassment based upon the description that they read. Was the description that they read from the point of view of the victim of the sexual harassment, or was it from the point of view of the perpetrator of the sexual harassment? So were you placed in the victim's shoes, or were you placed in the perpetrator's shoes? And what they found was that you were much more likely to identify a situation as sexual harassment if you were in the victim's shoes, and much less likely if you were in the perpetrator's shoes. That's very interesting. However, we have no idea what is the mean level of sexual harassment perceived in the perpetrator's population, or what is the mean level of sexual harassment perceived in the victim's population. So very interesting populations, we don't know anything about them. So what this experimenter did was they said, all right, we want to learn about these populations, so let's take a sample of subjects and we'll put them into, for example, the perspective of the perpetrator. So they pull out that sample of subjects and they found that it had a certain mean and it had a certain standard deviation. That sample of subjects had a certain mean and a certain standard deviation. The challenge, though, is that we don't know where these subjects came from the population. We know where they are because we measure them. They're our subjects. But we don't know if they came from, for example, the center of the population, or if they came from an extreme end of the population. And again, we don't know this because we don't know what the population is, right? So we don't know if they came from the center of the population. We don't know if they came from the edges of a population. We don't know anything about where they came from in that particular population. So this is the challenge when you're taking a look at a sample from a population. We don't know where from that population it came. So we don't know where the sample came from, but we do know certain things about the types of samples that can come from a population. And we do know that a sample such as this one over here is much more likely to occur than a sample like this one over here from the extremes. So there's way more people in the center of a population that's normally distributed that you can take a sample from, and there's way fewer people in the tails of a population. So it's much less likely that your sample is made up of people from the tails versus people from the body of your population. So samples can come from different portions of the population, and you can actually create what's known as a distribution of sample means. And the distribution of sample means is a new distribution, a distribution of sample means, and it's a collection of all the sample means from a particular population for a particular size of a sample. It's every single sample that you can get from that population for a particular size of a sample. So this distribution of sample means comes from the population distribution, but is not the same as the population distribution. So this is the population. So keep this infographic in mind. If this is the population, it is made up of individuals, right? So this distribution line is made up of hundreds of thousands, maybe millions, maybe billions, depending upon how big your population is. But it's made up of individuals, right? Individuals living in their little apartment buildings. That's the population. You can take a sample from that. You can grab some of these individuals, and you'll end up with a sample from that population. If you keep grabbing sample after sample after sample after sample, and you measure the mean of those samples, then what you can build is you can build this distribution of sample means. And it's important to remember that in this distribution of sample means, that each point, each little dot in this distribution is actually the mean of a sample. So instead of having individuals in these little apartment buildings, what you have is you have samples in these little apartment buildings. It's almost like you have roommates with everybody that is part of your sample. So every single time that you do a sample mean, you build up this distribution, but it's a distribution of samples, right? It's a distribution of samples of a certain size, and that's what this distribution is made up of. So we have your population made up of a distribution of individuals, and then we have a distribution of sample means made up of a distribution of sample means made up of the distribution of means of a bunch of people that created these different samples. And the big reason you have to distinguish between these two is because these two are not equal. So you can't use one in place of the other. Most importantly, you cannot use your population distribution to compare your sample to. All right, so distribution of sample means. Let's revisit a little visual of this with the dice rolls. So let's say that we were interested in gambling and gambling probabilities. This is exactly what gamblers and mathematicians used to do. So Many forms of gambling are very complicated. They do not avail themselves easily to probabilistic equations and math formulas. So one way that interested people have analyzed these games of chance is to just run them over and over and over and over and over again. Take a look at the population of outcomes for these games. So let's say that you are interested in dice rolls. The population of dice rolls for six-sided dice that are fair from the time the first dice was rolled to the latest dice roll that ever occurred, if you were to take that entire population of dice rolls, add them all up and divide by the billions of dice rolls that it was, you would find that the mean for that population was 3.5. If you were then to take a sample of a single dice roll, you would find that on average, the mean of your samples is also 3.5. So if you had samples and you took a look at the mean from those samples, you roll that first dice, right? Roll number one, sample number one. We're only dealing with one dice. You roll it, it's a 5. The mean for that sample is 5. Roll it again. Roll number 2. If you roll a 3, the mean for that is a 3. Roll it again. Number 3. If you roll a 1, the mean for that sample is 1. And you keep doing it and doing it and doing it until you have roll number, I don't know, infinity. Let's do that. Where you get a 6. If you were to then take the average of all of those sample rolls, you would get a mean of 3.5. So notice that this table of sample means, this distribution of sample means, very interestingly, has the same mean as the population mean. So that's going to be something that is true for every distribution of sample means. Your distribution of sample means has the same average as your population mean. So there's the population distribution for dice rolls that occur. So 1, 2, 3, 4, 5, 6, all occurring with a relative frequency of 1, meaning that they all occur with approximately the same frequency. If we were to plot our distribution of sample means, you'll notice that it looks exactly the same. And that is the one and only time that this will happen, when you have a sample size of 1. So your population distribution is a distribution of individuals. When your sample size is 1, each of your samples is also an individual, right? Sample size of 1 is a single individual for a sample. So if you have a sample size of 1, your distribution of sample means is a distribution of individuals. And that is the only time where it's the same as your population distribution. And that is it. So in every other instance, as soon as you have more than one sample, like more than one subject in a sample, like if we roll 2 dice rolls, your distribution of sample means changes from your population. So for 2 dice rolls, what you do is you roll your first sample, you roll your first 2 dice, you get a 5 and a 3, the mean of that is 4. You roll your second pair of dice, you get a 3 and a 3, the mean of that is 3. You rolled your third pair, you get a 1 and a 6, the mean of that is 3.5. You keep rolling it. For the last one, you get a 6 and a 4, the mean of that is 5. Right? So you have a sample mean for every 2 dice roll that you do. You have a distribution of sample means, and lo and behold, the mean of your distribution of sample means is still 3.5. It's still the same as your population distribution's mean. However, it is now no longer the shape of your population distribution. So as soon as you go to a sample size of 2, as soon as you let one extra roommate into one of these apartment buildings, your distribution of sample means changes shape and changes from what the population distribution is. I mentioned this, and I'll keep mentioning it a few more times, because the biggest mistake that students make in chapter 6 is they'll use the population distribution when they're supposed to use the distribution of sample means. So please just make a note, they're different. And as soon as you have a sample of 2 or more, you have to use the distribution of sample means and forget about the population. All right, so that's the distribution of sample means for 2 dice rolls. If we increase it to 3 dice rolls, you roll 3 dice, you add up the numbers, you divide by 3. We would notice that the mean for our distribution of sample means is still 3.5, but notice that our shape has once again changed. So the shape of the distribution of sample means is dependent upon the size of the sample. And as that sample size continues to increase, the mean for the distribution of sample means does not change. So this one is still staying at 3.5, but the shape of that distribution of sample means is changing. And as you can see, as we keep adding more dice, aka more subjects, that shape of the distribution of sample means, also known as a sampling distribution, is getting more and more like a normal curve. All right, so that's our distribution of sample means. And just one last time, not the same as the population distribution. You cannot use the population distribution in place of the distribution of sample means. So from here on out, we're dealing with samples. We have to compare a sample to a distribution of sample means. All right, so that's the theoretical way to get a distribution of sample means. You just collect samples from the population over and 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 over again. In the real world, we can't do that, right? In the real world, we have time constraints, we got budget constraints. I can't keep running samples of 20 subjects from the population, hoping that one day I'll run every combination of 20 subjects from the population, because we're literally talking billions of samples. So we usually only ever run the one sample. So how do we figure out this distribution of sample means if we can't run and measure the multiple samples required to build it? So that's what we're going to do today. That's the new part today. How do we figure out this distribution of sample means? So determining the characteristics of the distribution of sample means, we go once again back to that little bit of mathemagic that I like to, well, everybody calls the central limit theorem. And this basically tells us how to go from a population and population information to your distribution of sample means. So for any population with a mean of mu and a standard deviation of sigma, that's very important, that first statement there. For any population, which means that there is no population that is out of bounds for the central limit theorem, which means that there's no population that's out of bounds for psychology. So you want to do a psychology study on single fathers who were married to somebody with a drug addiction and are now single parents to a child with autism who is transitioning, is a transgender individual who's transitioning. If you want to do research on that particular population, central limit theorem fits. The central limit theorem applies. So for any population with a mean of mu and a standard deviation of sigma, the distribution of sample means from a sample size of n, so you need to know what your sample size is, will have a mean of mu and a standard deviation of sigma divided by the square root of n. So 2 pieces of information here. Number 1, the mean of your distribution of sample means will be the same as the mean of your population. That makes it a little bit easier as a student because half of the work is already done. As soon as you have the population mean, you have the mean of the distribution of sample means. So if somebody says, hey, my population mean is 100, you can be like, oh, well, my distribution of sample means has a mean of 100. Oh, my population mean is 15. Oh, well, the mean of my distribution of sample means is 15. Oh, my population mean is 482. Well, the mean of my distribution of sample means is also 482. So it's the same as the population. The key difference, though, and where you got to be really careful to make sure that you do this calculation, is that the standard deviation of your distribution of sample means is the standard deviation of your population divided by the square root of the size of your sample. That is the key move that you need to make. So if your distribution of sample, if your population has a distribution, I'm trying to multitask here and apparently failing miserably. All right, so if your population has a standard deviation of 25, yes. Standard deviation of 40. All right, let's do that. So your population has a standard deviation of 40. You have a sample size of 25. Okay? Population standard deviation of 40, sample size of 25. What is your distribution of sample means? Standard deviation. So we go 40 divided by the square root of the size of your sample, 25. That equals 40 divided by 5. That equals 8. One way to kind of help remind you of this move is that the distribution of sample means will always have a standard deviation that is smaller than the population. So the distribution of sample means is always more squeezed together than the population is. And what's more, the bigger your sample, the more squeezed together your comparison distribution is. The more squeezed together this distribution of sample means is. And as we're going to see, when something is more squeezed together, differences are easier to detect. When something is more squeezed together, the research hypothesis is more likely to be supported. So psychologists love to have big samples because those big samples squeeze together their comparison distribution. So if you have a sample size of 25, the distribution of sample means has a standard deviation of 8. It's been squeezed together. If you can up that sample size to 100, then we have distribution of sample means is 40 divided by the square root of 100. That's 40 divided now by 10. And we've just squeezed it in half. And we've got it down to a standard deviation of 4. So the bigger your sample, the more squeezed in your comparison distribution gets, the more easy it is for you to detect a difference in your experiment. So remember this move. That standard deviation divided by the square root of the size of the sample. Don't ask why it's the square root. That is grad school statistics. But just remember, it is the square root. So it's going to squeeze in that comparison distribution standard deviation. So it's the standard deviation of the population divided by the square root of the size of your sample. Yep?
If the standard deviation is smaller, how is it easier to tell the differences?
It's a good question. So if the standard deviation is smaller, how is it easier to tell what the differences are? So if you have a sample with a certain sample mean, that sample mean is going to give you a z-score, right? So if you have a z-score, we're not actually going to have any numbers on this, but let's say that you have a z-score of, we'll go with x, all right? So let's say that you have a z-score of x, and it's somewhere over here on your comparison distribution. If you have a cutoff score that's right about there, well, it's not a big cutoff score. Let's make it one where you missed. Let's say that that's your cutoff score right there. So you have 5%. We'll do this one-tailed. You have 5% of your distribution on this side, right? And your mean for your sample didn't quite make it into the tails, right? Didn't quite make it into the tails. We don't get to reject our research hypothesis. We accept the null hypothesis. Our treatment is ineffective. If we can take this whole thing and squeeze it in, what happens is that our entire distribution, oh no, I don't have any other colors. Left all my markers upstairs. If we take this and we squeeze it in, our comparison distribution gets thinner. And what that means is that 5% is now been squeezed in as well. So that squeezing in doesn't move our sample. Our sample's not going anywhere. Our sample is measured. That's what it is. But when we squeeze it in, that squeezing in moves our sample past onto the other side of the tails, and that's what we mean by it's easier to detect the presence of a treatment result. So again, if the cutoff score was over here and our sample missed it, if we up the size of the sample, even if our sample score doesn't move, so let's say that our sample averaged 40 after 25 subjects, and then we ran 100 subjects, and our sample mean was still 40, right? So the sample mean didn't change. What happens though is that comparison distribution gets squeezed in, so that same sample mean will now end up into the tails of the distribution, and we can reject our null hypothesis. So that's why it's more likely to detect results when you have higher numbers of individuals. Even if your sample mean does not change, your comparison distribution gets squeezed in, so you need less of an effect in order for that to be detected. All right, so we have that distribution of sample means with a certain sample size. We'll have a mean of mu, same as the population, but very importantly, have a standard deviation that is different from the population, standard deviation that is squeezed in, that is sigma divided by the square root of the size of your sample. So the standard deviation of the population divided by the square root of the size of your sample. And then the last thing that we need, or that the central limit theorem gives us, is that this distribution of sample means will approach a normal distribution as the size of your sample gets bigger. So we want to have a normal distribution because that's what's in the back of our textbook, right? Appendix A1 is a normal distribution. And if we needed statisticians to come up with distributions for every single population that's out there, statistics and psychology would once again be impossible to do. There would just be no way of knowing what all these distributions look like. Thankfully, however, through the magic of that central limit theorem, as soon as you start taking samples, your comparison distribution changes into a normal distribution. And it really doesn't take a sample size to get too big before you start seeing this normal distribution. So if you remember this, if you have a population distribution that is a flat population distribution, no body, no tails, it's just a unimodal flat distribution. If you take a sample size of 1 from that distribution, that's your distribution of sample means, which tells us that if you didn't know what that looked like, you would have no idea what this looked like, and you would not be able to do statistics. And that's why people who run statistics and do psychology studies do not like to use sample sizes of 1, because you never know what you're looking at. If you don't know what the population looks like, you certainly don't know what your distribution of sample means looks like. But as soon as you take a sample size of 2, sample size of 3, sample size of 4, sample size of 5, with just a sample size of 5, you can see that this distribution of sample means is now looking a lot like a normal distribution. And what that means is that we know what it looks like. It looks like a normal distribution, which means we can flip to table A1 and we can do statistics and we can do psychology. We have no idea what this might look like, But after just 5 subjects, we know that we're starting to get that normally shaped distribution of sample means. And it works regardless of what the population looks like. So there's your population distribution, sample size of 1, sample size of 2, 3, 4, 5. And once again, with this weirdly shaped population distribution, after just 5 subjects, we're starting to get a very normal looking distribution of sample means. And of course, most psychologists go higher than that. They'll do like 20, 30 subjects. So you can imagine exactly how close to a normal curve it can get. But once again, it doesn't matter what your population looks like. It doesn't matter how it's distributed. It doesn't even matter if you know what it looks like or how it's distributed. As soon as you start taking a sample of 2, 3, 4, 5 subjects, you start getting a distribution of sample means that is turning into a normally distributed distribution, which means that you can open up that textbook, flip to that appendix, which means that statistics applies, which means that psychology can be done. So it approaches that normal distribution as the size of your sample approaches infinity, and that lets us do statistics because we only have to take a look at one distribution in order to do a hypothesis test, and that's why Appendix A1 is where it is. It's the distribution that occurs most often. All right, any questions on that so far? All right. So just to kind of foreshadow what we're going to be dealing with for the rest of the semester, we're going to start off with this distribution of sample means. There's 2 more types of distribution of sample means, very much like this, kind of follow the exact same idea. So don't get thrown off when we get to those. It's a distribution of sample means approaching that normal shape as your size of your sample approaches infinity. All right, so I like to use this kind of way of thinking about the central limit theorem. So any population, mean of your distribution of sample means will be the same as your population. Standard deviation will be your population standard deviation divided by the square root of the size of your sample, and the shape will approach a normal distribution as the size of your sample increases. What we're going to do now to finish off today is I'm going to go over the way that the textbook explained this, just so that we can see that once. Nothing is different. It's exactly the same idea, but I have found that some students get a little bit confused with what is in their textbook. So you can do it this way, but let's go over what's in your textbook and I guess just get another perspective on this, determining the distribution of sample means. All right, so rule number 1, the mean of a distribution of sample means is the same as the mean of a population of individuals. So that's what we were talking about, where the mean of this population of individuals is going to be the same as the mean of your distribution of sample means. So this is what I don't understand. I don't know what this is supposed to be. This is like your population mean of means. So in your textbook, this is your distribution of sample means. This is your population distribution. So what it's saying here is that the mean of your distribution of sample means is the same as the mean of your population. It'll write it out like this. So the mean for the distribution of sample means is the same as the mean for your population. That's why I mentioned that it's not, as in knowing the distinction is not as vital for this step here. Because if you're doing your homework or if you're doing some statistics, if you're doing your exam and you're rushing through it and you mistakenly use the population mean instead of the distribution of sample means mean, you're not going to make a mistake in that case because they're the same. All right, so make sure that, think about it in the right way. You're looking for the mean of the distribution of sample means, but it's the same as the population mean. And that's rule number 1. Where it gets massively important is rule number 2. So we'll start off with 2A, which is about the variance. And the variance of the distribution of sample means, how wide or how narrow that comparison distribution is the variance of the population divided by the number of individuals in the sample. So your variance for your distribution of sample means is the same as the variance of the population divided by the size of your sample. In other words, the variance of your distribution of sample means is the same as the variance of your population divided by the size of your sample. So that's variance. And remember that the square root of variance is standard deviation. So that's where rule 2b comes from, where it says that the standard deviation for the distribution of sample means is the same as the standard deviation of the population divided by the square root of the size of your sample. So that's where that square root comes from. We just take the square of the variance and we end up with the standard deviation of your distribution of sample means equals the standard deviation of your population divided by the square root of the size of your sample. And I've called this the standard deviation of your distribution of sample means. It is the standard deviation of your comparison distribution. So remember, your distribution of sample means is your comparison distribution. But this term here is so important and it's so widely used and it's so fundamental to everything that's going forward that it's actually given its own name, and it's known as the standard error. So this is another foreshadowing clue in terms of how important it is to remember to calculate your standard deviation for your distribution of sample means. It's so important it gets its own name. It's literally just the standard deviation of the distribution of sample means, but it is so vitally important that statisticians said, let's call this the standard error. It gets its own name. So be forewarned, this is the key, crucial, important step. All right, and then the final step, rule number 3, that one's pretty easy. The shape of your distribution of sample means is going to be approximately normal if either of the following is true. So either your sample size is 30 or more. So 30 is, different people have different cutoffs. The cutoff in your textbook is 30. So regardless of what the shape of your population is, as long as you got 30 subjects in your sample, your distribution of sample means is a normal distribution. So once you get to that sample size of 30, remember this was just a sample size of 5, but once you get to that sample size of 30, then regardless of what your population looks like, you're dealing with a normal distribution for your distribution of sample means. The other time that you can know that you're dealing with the distribution of sample means that's approximately normal is if you're starting off with a distribution, a population distribution that is normal. So for example, IQ scores are normally distributed in our population. So if I had a sample size of 3 individuals, if I only got 3 individuals to participate in my IQ experiment, I know that my distribution of sample means is normally distributed because I know what the population distribution is. It's also normal. So if your population is normal, then your distribution of sample means will have a normal size, or normal shape for any sample size. If your sample size is 30 or more, then regardless of how this looks, this is going to be normally distributed. Your distribution of sample means will be normally distributed. So that's another reason why psychologists like bigger sample sizes, because the bigger your sample size, the more normal your distribution is going to get. All right, so any questions on determining the characteristics of your distribution of sample means? All right, so one more time, remember we are dealing with 3 separate and distinct distributions. We have our population distributions, our distribution of individuals living in their own apartment buildings. This distribution right here of individuals. We have our sample distribution. So when we take a sample out of this population, that sample will have its own distribution. It'll have its own frequency table. And then lastly, we have our distribution of sample means. Our apartment building filled with samples, filled with roommates living together. All these means making up that distribution. That is your comparison distribution right there. So when you're doing your hypothesis test and you get to step 2 and the question says something like, let's leave this right here. So if the question that you're reading says that you have a sample of 16 individuals, so we have a sample size of 16, and we got a sample mean, and let's say that they say something like, oh, you got 16 individuals, they were given a test of spatial awareness where they scored an average of 76.4. The population mean on this test is 70. And the population standard deviation is 20. Do your hypothesis test, right? Use a two-tailed test with an alpha of 0.05. So you do your research hypothesis, you do your null hypothesis, then you need to do your comparison distribution. They will not give you your comparison distribution. That is for you to calculate, to figure out. The worst thing you can do is just look for any mean and any standard deviation and say to yourself, I got this z-score formula burning a hole in my pocket, which is the sample mean minus the comparison distribution mean divided by the comparison distribution standard deviation. These symbols look close enough. I might use them. Don't. That's a mistake. It's the most common mistake. So please don't do it. Let's make it the most rare mistake. So what you need is you don't use your population numbers ever going forward. Population numbers do not get used in that formula over there. What you need to do is you need to figure out your distribution of sample mean numbers. So the easiest one is your distribution of sample means. The mean of it is going to be the same as your population. So the mean of it is 70. The standard deviation, that's super important, standard error, equals the standard deviation of your population divided by the square root of the size of your sample. So if you do not divide by the square root of something, things have gone horribly wrong. So we need to figure this out. So it's 20 divided by the square root of 16. That's 20 divided by 4. And that equals 5. So now, when you're figuring out your sample's z-score on the comparison distribution, you sub in the mean for your sample, 76.4. You sub in the mean for your comparison distribution. Remember, not using the population. Mean for the comparison distribution, same as the population. And that's where I think some students get tricked. Because they're like, oh, it's the same as the population, we'll just use the population. No, don't do that. Because when you get down here to the standard error, that standard deviation, no to this, yes to this, and that's the one you have to divide by. So again, if you're not dividing by the square root of your sample somewhere when you're doing your homework, you're doing it incorrect. So make sure that at some point you're calculating out that standard error. Make sure that at some point you're hitting that square root, key on your calculator. I'll be honest with you, you're going to get a lot of sample sizes that are perfect squares. That could also be your clue. All right, so get ready for a lot of sample sizes of 16 and 25 and 36 and 100 and 81 and 169. Those are the sample sizes you're going to be dealing with in Chapter 6. Take the square root of it and divide your population standard deviation by that amount. All right, so that's all that I wanted to cover for today. Any final questions on that? Make sense? All right, so now you have the full set of skills that are required. So as always, we're doing new pretest. We just had our exam, so you got your new pretest coming in. If you don't get 100% on any of your pretests, go to the MyStat Lab study plan, find those mastery points, earn 100% on the mastery points, and I will correct your grades to 100% on your pretest. I didn't get a chance to update those grades yet for the ones that were done before exam 2, so I'll get to those over the next few days. And just a reminder, you are now ready to go on homework assignment number 9 for chapter 6. So homework assignment, the homework assignment for chapter 6, much like the homework that you were doing in chapter 5, the one big difference is now you're dealing with samples. So you're going to probably have to do this move when you're doing your, well, you're definitely going to have to do this move when you're doing your hypothesis testing. So when they give you the mean of the population and the standard deviation of the population, if they do not specifically give you the distribution of sample means or comparison distribution numbers, remember you got to take that population standard deviation and divide it by the square root of the size of your sample. So look for that information, take your time, don't fall into the trap, and we'll see if we can get a whole bunch of people with 100% on homework assignment number 9. All right, other than that, that's all I wanted to cover for today. So if that's enough hypothesis tests with means of samples for you today, feel free to head out a little bit early. If you have any questions on anything, if you want to try to start out your homework and just give it a go here in case things go wildly wrong, feel free to call me over. We got about 20 minutes left in class, so if you need any assistance with anything, let me know and I'll come by to help. Other than that, we're done what I wanted to cover today.